Hello everyone. Today we will discuss many modern concepts in MOSFET theory, and one is this idea of ETSOI MOSFETs. We have seen a glimpse of it in our previous class when we discussed the geometric screening in MOSFETs. Second, we will discuss in some detail about the quantum confinement in MOSFETs. And third, a modern technique to enhance the performance of devices, and that is known as strain engineering, which essentially uses strained silicon in channel to have more mobility of electrons. So that's what we will see, and before going into these details, let's quickly have a look at what we have seen so far. So what we discussed in our previous class was that for smaller devices, for nano MOSFETs, we need to consider 2D electrostatics, because in addition to the electric field in y direction, the electric field in x direction is also prominent, and moreover we observe what is known as DIBL, drain induced barrier lowering, which essentially means that in nano devices the threshold voltage is decreased as the drain voltage is increased. Secondly, it has been observed in small channel MOSFETs that the threshold voltage reduces as a function of length. So as the channel length reduces, the threshold voltage also reduces, and this is known as the threshold voltage roll off, which means that the threshold voltage goes down below a certain channel length. And in order to account for all these things, we need to consider the 2D electrostatics, and in 2D electrostatics we take the 2D Poisson equation and we solve this in the channel of the MOSFET, and what we obtain is that the 2D Poisson equation can be approximated by the 1D Poisson equation, but now the doping in the channel needs to be replaced by effective doping, and this effective doping, Na effective, is less than the actual doping of the channel. So by considering the 2D electrostatics, we can account for all these effects that arise in the small channel MOSFETs. Second, in order to mitigate these bad effects, or in order to maintain the consistency of our devices, we use a technique called geometric screening, and geometric screening is another form of screening, and the screening in materials with mobile charge carriers is that when a charge perturbation is produced, mobile charge carriers rearrange in such a way that after a certain distance the effect of the charge is negligible, and in presence of mobile charge carriers we need to use the screened Coulomb potential relationship. So that's what the expression for the screened potential, screened Coulomb potential. And the geometric screening in geometric screening technique, what we essentially need to do is we need to neutralize, or we need to avoid the drain electric field lines to reach to the source electric field line. So we need to stop the drain electric field lines to reach to the source electric field, and in order to do that we need to sort of cover the channel with gate from as maximum number of sides as possible, and that's why these kind of geometries, also known as double gate SOI geometries, in which instead of bulk silicon we use silicon on insulator, which is a silicon on a buried oxide, and we can use single gate ETSOI techniques. We can make single gate ETSOI MOSFET, which looks like this, SG-ETSOI MOSFET, and this is DG-ETSOI MOSFET. So generally in ETSOI techniques, in SOI techniques, there are two broad categorization. One is the PDSOI technique, partially depleted silicon on insulator, and second is FDSOI technique, which is fully depleted silicon on insulator. So as the name suggests, in FDSOI the channel is fully depleted, and FDSOI is an extremely thin silicon on insulator, and this is essentially FDSOI MOSFETs. This is single gate, this is double gate, and as is clear from the figure, the geometric length, the geometric screening length in DG-ETSOI MOSFET is smaller as compared to the single gate ETSOI MOSFET. Okay, and in this series, in order to use geometric screening technique to avoid DIBL and threshold voltage roll off, a novel geometry of MOSFETs was suggested in in 1980s, 1990s, and that was used in making small channel MOSFETs, and this is known as FinFETs, in which the channel is a vertical channel now, and the channel is surrounded by the gate on 3 sides. In some cases, in some geometries, the channel can be surrounded by the gate from 4 sides as well. And so generally what we try to do is we try to make sure that the channel length is at least thrice of the geometric screening length in order to avoid any change, any inconsistency in the threshold voltage arising due to the low channel length. Second concept that we started was the concept of quantum confinement, and by a rough calculation, what we calculated was that the de Broglie wavelength of electrons in these materials is around 6 nanometers at room temperature. So if the electrons are confined in this kind of dimension, so if the electrons are there in a material which is 5 to 10 nanometers, in that case the material length is of the order of the de Broglie wavelength, and in that case we need to consider the quantum mechanical nature of the electrons. So this quantum confinement idea, this we will see after a bit. First let's analyze a little bit of let's do a bit of analysis of the DG-ETSOI MOSFETs. So the DG-ETSOI MOSFET comes from the ETSOI technique. ETSOI means extremely thin silicon on insulator, and in this case the MOSFET looks like this. The active region of the MOSFET looks like this, in which the channel region is an extremely thin silicon on insulator, and on both sides of the channel, on the top and the bottom side, we have the gate electrodes, and on this side we would have source, on this side we would have drain. Okay, so this is how the channel region of the DG-ETSOI MOSFET looks like. DG-ETSOI MOSFET, in fact, double gate extremely thin silicon on insulator MOSFET. So this kind of MOSFET offers an advantage of having good very small geometric screening length, so that we can make very small channel lengths. Generally this kind of MOSFETs are used in around 20 nanometer channel length or so. Okay, so in this DG-ETSOI MOSFET, generally the ETSOI structure is undoped. When we use an extremely thin silicon on insulator, the ETSOI structure is undoped. And here now what we will try to do is we will try to understand how the charge in the semiconductor varies with the potential in the semiconductor. So the kind of analysis that we did for the MOSFET, we will try to do that kind of analysis for DG-ETSOI MOSFETs. What it means, we will try to understand QS versus psi S, and finally we will try to understand psi S versus VG. Because VG is the external voltage that we apply on the MOSFET, psi S is the voltage that appears at the surface of the semiconductor, that appears at the interface of the semiconductor and oxide, and QS is the charge in the semiconductor. Okay, and as is visible from this figure, there are 2 gates here, and in DG-ETSOI MOSFET structures, what we can do is or what we can assume is that the charge in the semiconductor or what we can say is that almost half of the charge in the semiconductor is mirrored by the upper gate and half of the charge in the semiconductor is mirrored by the lower gate. Typically the thickness of this silicon layer is around 5 to 20 nanometers. Okay. And so the total semiconductor charge can be considered to be divided in two components. Half of the charge is mirrored by the upper gate, half of the charge is mirrored by the lower gate. So in this case, if we try to understand what is the total charge in the semiconductor, and if this ETSOI structure is undoped, in that case the charge due to depletion depleted, since now no dopants are there, so this depletion charge is extremely low, and the only charge that is there is because of the mobile holes and electrons. The depletion charge appears because of the uncompensated dopant atoms, and in this case the uncompensated dopant atoms are not there. So this charge, the depletion charge is negligible, I would say, is not there, and the total semiconductor charge is just because of the mobile holes and electrons. It's just because of the holes and electrons, and so that's why we can write the total semiconductor charge to be Q times number of holes minus number of electrons in the semiconductor. And now the number of holes and electrons in semiconductor are function of the semiconductor potential. If the number of holes without any semiconductor potential is Ps naught and number of electrons without the semiconductor potential is Ns naught, which means when there is no gate voltage, the number of holes in the system is Ps naught, and when there is no gate voltage, the number of electrons is Ns naught. When we apply a gate voltage, and generally the same gate voltage is applied on both the gates, so both the gates are sort of connected to each other. In that case, a semiconductor potential psi s appears at the interfaces. Okay, and in that case what happens is that the number of holes and the number of electrons get modified. So now with psi s potential, if the potential is positive, the holes will go down, number of electrons will increase, and if the potential is negative, the number of holes will go up and number of electrons will go down. This we have also seen in our discussion of the conventional electrostatics of the MOSFETs. So in presence of a semiconductor potential, the total number of holes and electrons are Q times Ps naught exponential minus Q psi s by Kt minus Ns naught exponential Q psi s by Kt, okay, as is written here. Okay, so now let us assume that when the semiconductor potential is 0, which means we are operating at a reference potential. In that case, Ns naught and Ps naught is equal to the intrinsic carrier concentration of electrons and holes in the silicon, in the semiconductor essentially. So, so Ns naught and Ps naught will be equal to Ni or N silicon, and that's what we will replace in here. So this expression of the semiconductor charge becomes Q times N silicon, intrinsic carrier concentration in the silicon, times exponential minus Q psi s by Kt minus exponential plus Q psi s by Kt. So this is the total charge per unit area in the channel in this DG-ETSOI MOSFET. So this is DG-ETSOI MOSFET, just to sort of emphasize this. And now if we draw a relationship between the mobile charge, which is essentially the total semiconductor charge. So now if you recall, the total semiconductor charge is the depletion charge plus mobile charge. In this case it is not there. Qs is equal to Qn, and that is equal to this number. And if we plot log Qs as a function of psi s, which means we want to understand the dependency of the semiconductor charge on the semiconductor surface potential. In that case, that looks like this. If we plot log Qs versus psi s, up to a certain psi s, these exponential, so for example, if we are looking in the positive psi s regime, in that case, this will be almost 0, this negative part will be 0, because it will be a negative exponential, and only this will be there, only this will be there for positive psi s. This will be almost 0 for negative psi for positive psi s. So it will be a log of Qs will be just directly will be proportional to psi s. So it will be a line after a certain psi s. Below this psi s, generally it is extremely small value, so it is not shown here, but it should be something like this. Similarly, on the negative side, the second term will be 0 and only the first term would be there, and it will be almost the same kind of plot. So this will be the charge versus semiconductor potential relationship in the case of DG-ETSOI MOSFET. So as if this, so this is quite close to, or if we compare this to the charge versus Qs versus psi s relationship for the MOSFET, in that case, in conventional MOSFETs, in addition to Qn, we also have Qd. So we have this kind of relationship there, and in this side we have this kind of relationship. Okay. So this is somewhat different than the conventional MOSFETs. Now, what is the mobile charge sort of in the DG-ETSOI MOSFET? The total charge in the semiconductor is just the mobile charge, and if we assume in the inversion region, which means we have applied a positive potential, and so N type of channel has been formed in the silicon. This has been inverted and now this has become N type. In that case, this this term, first term would be 0 and only this term would be left. So this will be the mobile charge in the DG-ETSOI MOSFET, and this will be equal to minus Qn silicon exponential Q psi s by kT. And so we can, what we can assume is, now we are trying to find out a relationship between psi s and Vg, because as I have already mentioned this, we can change Vg externally. So Vg is in our hands, and psi s is the potential that appears on the semiconductor interface, and this psi s essentially governs the charge or electrostatics in the MOSFET. So in addition to this relationship, we would also like to understand this relationship. And whatever mobile charge is there in this DG-ETSOI MOSFET, we can assume that half of the charge is or semiconductor images, half of the charge of the semiconductor is imaged by the top gate and the other half is by the bottom gate. So in that case, what happens is, in that case we can see what is the charge across these top and bottom oxides essentially. Because if you remember the basic relationship between Vg and psi s, Vg is delta V ox plus delta V semiconductor and delta V ox plus psi s. So we need to know what is the voltage drop across the oxide, and in order to know the voltage drop across the oxide, we need to know what is the voltage across the voltage on each sides of the oxide. So here, if the total charge in the semiconductor is Qn, we can assume that Qn by 2 is there for the top gate and Qn by 2 is there for the bottom gate. And using Gauss's law as we did before, we can find out delta Vox. So delta Vox is minus Qn by 2 divided by Cox, because Qn by 2 is the charge, Cox is the potential capacitance of the oxide on each side. So that essentially gives us Vg prime is equal to minus Qn divided by twice Cox plus psi s. Okay. And just to sort of remind you, this prime is there because we are not writing down flat band voltage here. If we explicitly consider the flat band voltage, in that case we can just write Vg there. Okay. And the most important, or one of the most important regions of MOSFET operation is the subthreshold region. So below subthreshold, even this charge is not significant. As we have also seen in the previous plot, in the previous slide, this is the threshold, I would say the threshold condition. Below this, the charge is also insignificant. So below threshold here, what happens is even this charge is 0, and what we can say is that Vg prime is equal to psi s. So in DG-ETSOI MOSFETs, below threshold voltage, the semiconductor potential is almost equal to the, or is equal to the gate voltage, if we are not considering the flat band voltage. Otherwise, Vg will be VFB plus psi s just, or Vg prime is equal to psi s. And that's an important relationship, because in bulk MOSFETs what happens is that psi s is equal to Vg by m, or Vg prime by m, to be more precise, and where m is always greater than 1. We try to minimize m, we try to bring m as close to 1 as possible, but it is not, we cannot do it all the time. But in DG-ETSOI MOSFET, this is naturally there. Naturally m is equal to 1, and that's why psi s is equal to Vg prime. So that's an advantage here, because all the voltage that we apply on the MOSFET drops across the semiconductor, in this case below threshold voltage. So in subthreshold regime, what we can say is that the gate has very good control over the channel. That's a very important part of this device operation here, because that gives us better performance as compared to the bulk MOSFET. So in terms of gate voltage, if we now represent the mobile charge, so the mobile charge is minus q times n silicon exponential q psi s by kT, and now psi s is just equal to Vg prime. So Qn can be represented in terms of gate voltage like this in subthreshold regime. So now the gate has complete control over the surface potential, and that is an advantage of DG-ETSOI structure. And if we compare the two plots, the plots for bulk MOSFET and DG-ETSOI MOSFET for psi s versus Vg relationship, what we see is that below threshold voltage in DG-ETSOI MOSFET, psi s and Vg prime are one and same essentially. In the case of bulk MOSFET, however, below threshold voltage, psi s closely follows the Vg prime line, but it is not exactly the same. It is somewhat different, but it deviates after the threshold voltage. Similarly, it deviates in the case of DG-ETSOI as well, and the deviation in the case of DG-ETSOI is even more. But we are mostly concerned about this regime, and in this regime DG-ETSOI MOSFET has better control over the channel. So the gate in double gate ETSOI MOSFET has better control on the channel as compared to the bulk MOSFET, and that's one of the main advantages of using DG-ETSOI structure apart from geometric screening. So that's why this is an important MOSFET technology, especially for nano MOSFET, especially for the sub 20 nanometer or 40 nanometer, that kind of channel length range. In that range, this is quite important MOSFET technology. And here we have seen the relationship between the charge in the MOSFET, the semiconductor potential and the gate voltage. Okay. Now let's come to an important concept in MOSFETs, which is the idea, or which is the quantum confinement in a MOSFET. And this topic we started in our previous class as well. But now since we have better understanding of ETSOI MOSFETs, so we would be able to do it in a better way. So as we saw in the last class, the electrons in the inversion regime, even in a bulk MOSFET, are in a potential well, and this potential well is like this. Similarly, in ETSOI MOSFETs, electrons are confined only in this distance, and generally the de Broglie wavelength of electrons at room temperature is around 6 nanometer. So if these confinements, if this ETSOI silicon dimension is 10 nanometer or around that dimension, or if this potential well is 5 to 10 nanometer, in that case we need to consider the wave nature of electrons, and we need to consider the quantization in this direction, or in this case quantization in this direction. So both of these directions are y directions. So, and generally what we observe is that the thickness of the inversion layer is few nanometers only, around 4 to 6 nanometer or of this range. So what we can say is that in the inversion layer, electrons are always confined in y direction, and we need to consider this kind of quantum mechanical confinement in MOSFETs, even in bulk MOSFETs. In ETSOI MOSFET, this confinement is there because of the geometry of the MOSFET as well. So that's what we will try to understand now. And so this is the kind of confinement that is there in bulk MOSFETs. This is the shape of the quantum well that is formed in the bulk MOSFET at the interface of the oxide and the semiconductor, and this is the kind of confinement that is there in ETSOI structures, or most of the SOI nanoscale SOI MOSFETs. This is the case, this kind of confinement is there. So now what happens is, because of this potential well, the electrons movement is confined in the y direction, and confinement leads to discretization of energy levels. So the electronic energy levels will be discretized in y direction, and they may be continuous in x and z direction. So in y direction what happens is, in this kind of potential well, the electronic energy levels are given by this value, as we have seen in particle in a box situation as well, that the energy levels are given as h bar square, m square, no, this is not m square, this is n square. There is a typo in that equation that is written there, n square pi square h bar square divided by 2 m star t square, where t is the thickness of the ETSOI MOSFET, or t is the thickness of the inversion layer as well. So we can generally, for the sake of better understanding, we can assume that even in bulk MOSFETs this kind of confinement is there. Although if we do a proper analysis in a triangular quantum well which is there in bulk MOSFETs inversion layer, there the energy levels are given by this relationship, various energy levels are given by this relationship. Yeah, okay. So what happens is that in y direction the electronic energy levels are discrete and they are given by this expression. In x and z direction, which is the transverse plane, in that plane electronic energy levels can be continuous. So, the total energy of the electron is given by the energy in xz plane plus energy along y direction, and that is what is written here as well. Now, something interesting happens here. If we closely look at the band structure of the silicon, these are the iso energy surfaces at the bottom of the conduction band, or these are the constant energy surfaces what it means is, if we plot all the k values, all the kx, ky, kz points, we have seen this before as well, but let me repeat it. If we plot all possible combinations of kx, ky, kz that give electronic energy close to or electronic energy equal to E, and if we plot all these k points, in case of silicon that gives us these 6 ellipsoids, and these are, that is why known as iso energy surfaces or constant energy surfaces, and this, for this particular case, it is this energy is close to the bottom of the conduction band. So, we always try to analyze close to the bottom of the conduction band because that is the point where most of the conduction takes place. So, close to the bottom of the conduction band, the iso energy surfaces look like this. And now in the channel, because of the quantum confinement, because of this kind of confinement, what happens is that electrons are confined in y direction, electrons movement is restricted in y direction, they are although free to move in x z direction. So, if we look at along y direction in this particular plane, in this direction the electronic mass or the longitudinal effective mass of the electron will be given by this curvature, because if you remember, the effective mass of the electron is inversely proportional to the d2e by dk square, basically ek curvature. In this case, this curvature is actually representative of d2e by dk square, and so in this direction the effective mass will be given by this curvature, and in xz direction the effective mass will be given by these curvatures, essentially these curvatures. So, as you can see in the longitudinal direction, longitudinal means along the direction of the confinement, the curvature is less, so the effective mass will be more. In the transverse direction, the curvature is more, so the effective mass will be less. So, that is why the longitudinal effective mass is 0.9 times the rest mass of the electron, and the transverse effective mass is 0.19 times the rest mass of the electron. So, what happens now is that because of these two kind of effective masses, now there are two kind of energy levels that are generated in the system. So, since we have two kind of electrons now in the system. One kind of electrons have double degeneracy because there are two ellipsoids in the longitudinal direction and their mass is more, and another kind of electrons have less mass, the transverse effective mass, and their degeneracy is 4 because there are 4 ellipsoids corresponding to the transverse direction. So, because of this difference, because of these two kind of electrons in the system, now we have two set of energy levels, two set of discrete energy levels, and for heavy mass the energies will be less, because if you remember, the energy due to confinement is n square pi square h bar square divided by 2 m star t square. So, energy is inversely proportional to the effective mass. So, for the heavy electrons, the energy levels will be low, and for light electrons, the transverse direction electrons, the energy values will be high. So, the heavy electrons energies are represented by these epsilon 1, epsilon 2, epsilon 3, and the light electrons energies are represented by epsilon 1 prime and epsilon 2 prime. So, these are the unprimed energy levels and these are the primed energy levels. Red ones are the primed, blue ones are the unprimed, and these are because of the confinement in y direction. Because of the confinement in the y direction, this degeneracy is now broken. In a bulk silicon, generally what happens is electrons are free to move in any direction. So, the total mass, so the total conductivity of the electron is the sum of all the conductivities or the average of all the conductivities, and that is why the net effective mass is the average of the conductivity is inversely proportional to the effective mass. So, if we in a bulk silicon, if we try to calculate the conductivity effective mass, it will be given by the average of the it comes from the, so the conductivity is, effective conductivity is sigma 1 plus sigma 2 plus sigma 6 by 6. It is the average of all the conductivities, and each of these conductivity is inversely proportional to the effective mass. So, this sigma effective can be written as 1 by m star effective, and all these. So, these 6 conductivities correspond to these 6 ellipsoids. So, in generally in any direction, the 2 ellipsoids have longitudinal effective mass and 4 ellipsoids have transverse effective mass. So, that is why the net effective mass can be written as 1 by ml plus, so the 2 have longitudinal and 4 have transverse. Like this. So, this expression actually gives us this kind of expression, and from here we obtain what is known as the conductivity effective mass of the electron, which is given by 1 by 6, 2 by ml plus 4 by mt, or 1 by m star is equal to 1 by 3, 1 by ml plus 2 by mt. So, if the longitudinal and transverse effective masses are given for a particular silicon wafer, in that case we can calculate the conductivity effective mass or the total effective mass of the electron, that we need to calculate conductivity by this expression. So, this is an important expression and this is true for bulk silicon. But as soon as there is confinement, because of now what happens is in one direction also there are 2 kind of electrons, and these the energies of these 2 kind of electrons are now inversely proportional to the mass. So, this degeneracy is lifted between the longitudinal effective mass electrons and transverse effective mass electrons, and that is why we will have 2 kind of subbands in the system. So, I would recommend all of you to go back and go through the class where we discussed the idea of subbands. How do we consider subbands in a quasi 2D material, and exactly the same thing is happening here, because here also we need to consider subbands, but now we have 2 kind of subbands. One is because of the heavy electrons having longitudinal effective mass, and one is because of the light electrons having transverse effective mass. Okay. So, this is the picture that is there in the case of confined electrons, in the case of quantum confinement in MOSFETs. So, please remember that in bulk silicon there is all these values are degenerate, but now in this case, because of the confinement, the degeneracy is lifted. Now, there are 2 different kind of subbands in the system. So, this is a summary of or this is the text to understand this phenomena, this degeneracy, the lifting of degeneracy because of the quantum confinement. I would recommend all of you to go through this text carefully. Okay. So this brings us to another an important idea in nano MOSFETs, which is the strain engineering. Strain engineering essentially means using a strained silicon, as I told you in the beginning of the class, to have better performance. And in strain engineering, essentially what we do is we apply strain, or generally let me give you an example of biaxial strain. Biaxial strain means that if this is the MOSFET, source drain, or let me draw ETSOI MOSFET. So we have this kind of structure, silicon is there, this is the silicon channel, source and drains are there, this is oxide, this is the gate electrode. Now the current in this MOSFET depends on how fast the electrons can go from source to drain, or what is the mobility of electrons in the MOSFET. So if you remember, in bulk MOSFETs, current is directly proportional to the mobility, and even in ballistic MOSFETs, current is directly proportional to the injection velocity at the top of the barrier. So in order to have a better current, better performance of the MOSFET at a given voltage, we would like to increase the mobility of electrons or the injection velocity of the electrons. And one of the techniques is to use strained silicon. Strained silicon means that instead of using a normal silicon in the channel, we now use a silicon whose lattice structure has been changed, and we will see that for certain kind of change in the lattice structures, the velocity of electrons, the injection velocity of electrons will increase. That will increase the current, drive current in the MOSFET, and that can give us better performance without scaling. So that's one of the modern techniques to enhance the performance of nano MOSFETs. And let me not start that this topic right now, because it will involve a longer discussion. So if we understand the idea of quantum confinement and how various subbands, or how two kind of subbands are formed, we can understand the strain engineering or the strained silicon as well. Please remember that these unprimed energies, they have degeneracy equal to 2, because they have 2 lobes corresponding to them. There are 2 ellipsoids that give us longitudinal effective mass, and the transverse effective mass is given by 4 ellipsoids, so their degeneracy is 4. Okay. So in any case, so generally in bulk silicon, what we do is we consider the top of the valence band and the bottom of the conduction band. But in the case of quantum confinement, or in inversion layer, or in ETSI MOSFET, in addition to these energy levels, we also need to consider the subbands. So we need to consider epsilon 1, epsilon 1 prime, and these essentially these energy levels. So the electrons will be occupied in the conduction band in these two kind of subbands. So please review the idea of subbands that we discussed while we concluded our discussion of the general model of transport, and then this idea of quantum confinement will be clear to all of us. So with this kind of background, with this background of quantum confinement in MOSFETs, our next topic of discussion will be the strain engineering, or how to use strained silicon to have better performance of devices. So that's what we will do in the coming class. Thank you all. See you in the next class.